Okay, now we're going to take a look at work's relationship with energy. So work enables us to know how much a force or a combination of forces changes the energy of the system. And so the example given in class is a roller coaster that starts from ground level and then accelerates this with a force and then sends it pretty much almost vertically straight up for about 300 feet and then ends up coming back down the other side. And so there's a major force over a displacement. There's a lot of work done. Even though this is a ground level and there's no kinetic or potential, it gains a lot of energy before it goes up the roller coaster ramp there. So work bridges between a force, which is a vector, and a scalar with energy, and we can multiply, the force times displacement times cosine of theta to find out how much force there is, or how much work there is. And we know that, again, that work changes mechanical energy, just like we saw with that roller coaster car. If it's starting from rest here and there's a force, it's going to speed it up and get it to increase in its kinetic energy. And so in this case, if the force is this way, the displacement's this way, it's cosine of 0 degrees, right? So you have positive work that's done on this, and it speeds it up. Now at the end of the ride, after it goes straight up and then it comes back down and it's going this way, it's got to come to a stop. So in that case, the force is this way, the displacement is this way. This would be cosine of 180. So you have negative work. And when that happens, this car, as it comes to a stop, has that force of the braking there. So we get to the work kinetic energy theorem, which states that the net work due to all forces equals the change in kinetic energy of the system. So what we do is we find out what the net work is. So in other words, this is force net times displacement times cosine theta, and then the delta Ke, that's Ke final minus Ke initial. Remember, delta is final minus initial, right? So 1/2 mv final squared minus 1/2 mv initial squared. And this is how we find the the change in energy of the system. We look at the net work, by getting whatever the net force is, and then solving it from there. Okay, so let's take a look at this first one. We have a soccer ball that's being kicked with 110 newtons of force, and in this case we're just going to assume there's no friction. 110 newtons of force, and his foot is in contact with the ball for 3 centimeters. So that is the only length that his foot is in contact with the ball, so 0.03 meters. And we want to find out what is the final velocity of the soccer ball, and really probably be better to say final speeds after the soccer ball is kicked. So when we do this, you don't have to write out the first equation, work net equals the change in kinetic energy, but you need to write down force net times displacement times cosine theta equals 1/2 mv final squared minus 1/2 mv initial squared. And this will allow you to look at the situation full. So we only, we have the normal force of gravity, which are balanced out, and then the force applied is the really only unbalanced forces. So that's our net force here. We have 110 newtons. Our displacement is only 0.03 meters. The displacement's to the right and the net force is to the right, so cosine of 0 degrees. And then 1/2, we have the mass, which is 0.4, times the final speed squared, which is what we're looking for, and then it's starting from rest, so this is 0. And so we're able to find out what the final speed will be after his foot is in contact with the ball for that 3 centimeters, and by looking at how much work impacts it here. And so we end up getting 4.06 as the final speed. Now, if it's a frictionless surface, this ball is going to continue at 4.06 as it goes along, right? So, yeah, as long as there's no friction, right? So if there was friction, it would start to slow down. There would be work going, negative work, because the ball would be going this way to the right, and then the force would be to the left, but in this case, no friction. Okay, so on this one, we do have friction, and the friction will play into the net force. So if we have the ball here, we have a force apply going forward, in this case 120 newtons, and we do have some friction acting here. Normal force, force of gravity, and then her foot is in contact with the ball for 4 centimeters, so 0.04 meters. And we want to find out what's the final speed of the ball. So in this case, you know, it's going to be different because we do have some friction that's playing into this. If we look at the forces in the y, you know, they have the positive normal force plus the negative force of gravity equals 0. And the net force is 0. There's nothing going on, no net work in the y. But if we look at the x, right, and this is where we have to set this up, we have the positive force applied plus the negative force of friction equals ma, and this is our net force in the x right here. So what we need to do is, we already know this is 120. We're going to have to add up the friction, which is acting in the negative, and the way we get friction is the coefficient of kinetic friction times the normal force, right? So we know the normal force in this case is equal to the force of gravity, which is mg, and we can solve for the normal force. Once we have that, we'll place that in here and multiply that by the coefficient, and that will give us friction. And then it's actually that value that we're going to use after we add those up together. I'll show you that here. So the coefficient times normal force, and the normal force is 3.92, and then we have the coefficient, which is this, and we end up getting a net force of 119.53. So it's not quite as much as it would be if there was no friction, right? So now that you have this, you can figure out what the final speed is if it's starting from rest. So why don't you go ahead and pause the clip, and then go ahead and calculate what the final speed will be, you know, after she kicks the ball, and then see if you're okay. So go ahead and pause the clip, and then when you're ready, you can continue. Okay, so we should get a final speed of 4.89 meters per second, and again, this will be not quite as fast as it would be if there was no friction. Okay, so now we have a situation with a hockey puck that's being hit with 65 newtons of force over 16 centimeters, and we have some friction here, and we want to find out the final speed if it's starting from rest. So on this one, it's going to be basically the same process. You have to set up the net force, you know, in the x, take a look at the forces in the y as well, and work through that same process to find the net force, you know, from here, net force. And then once you find the net force, you can take a look at how work net equals the change in kinetic energy. So once you work this one all the way through, and then you can continue the clip when you're ready. Okay, so we can set up our some of the forces for both, and we end up getting you know, the normal force equal to the force of gravity again. So the normal force is 2.254, which we place into our normal force here, multiplied by the coefficient, which is 0.04. So it takes away from the 65, you know, only 0.09 newtons is the friction, so not very much. And so this is the net force, and then with the net force we come into the work equals a change in kinetic energy. We should get a final speed of 7.5 meters per second. Now if we evaluate this one, we have a pack that's being pulled you know, at an upward angle here, and so this is a little bit different. The force applied is upward at an angle, and we are still doing work, but again, we'd have to break this up into the X and Y to think about what kind of work we're doing, right? So remember, the only work that you do is the work that's parallel, or where the force is parallel to the displacement. So if we break up this force applied, we have the force applied at an angle here is 125. We have the coefficient of kinetic friction, which is 0.07, and the angle's at 30 degrees. And yeah, we've got the mass here. So and it's over 10 meters. So the first thing we're going to do, we want to find out the net work, and then we can figure out, you know, what's going on with motion as well. So if we set up our other forces, we have the normal force, force of gravity, friction acting in the negative. So if we look at the forces in the X and Y, the forces in the Y, you know, we have the positive normal force plus the negative force applied, or plus the positive force applied in the Y, which is right here, plus the negative force of gravity. And then in the X, we have the force applied in the X and then the force of friction. And so when we place the trig in there, we have the angle is 30 degrees, and we can get what the force applied in the Y is here. You know, it's the hypotenuse times the sine of 30. This is the opposite side, right? It's the hypotenuse. For the force applied in the X, we have the hypotenuse times cosine 30. And then if you notice here, right, the normal force is not going to be equal to the force of gravity because we do have you know, some force in the Y, and we end up getting a normal force of 1093.9, which we can place in here for the normal force and determine what the net force is. So we've got 0.07 as the coefficient, and we should get a net force of 31.68. Now that we have this net force, and if you notice it's just in the X, right, there's no net force in the Y. All the forces cancel out and add up to 0, right? So when we calculate the work, we have the net force times the displacement, and this gives us our net work here. So you know, let's assume that this pack starts from rest and we want to find what is the final speed. We can do that again because we have the net work, right? So we can figure out what's going on with the motion, and we set up work net equals a change in kinetic energy. We have the net work. We're looking for the final speed, and we should get 2.32 meters per second.